Hopefully you've had a chance to try this practice problem. I'm going to walk through it now, the solutions. So if not, just pause the video and give it a try first. So what we're doing is we're going to consider two mixtures, and we're going to identify the solute-solvent interactions that'll form, as well as what's happening for just the solute-solute and solvent-solvent interactions that break. And then we're going to predict if the mixture will form an enthalpy of solution that's endothermic, exothermic, or ideal. And now we're not using numeric values for this. We're really just doing a comparison and then making an argument for what we expect it to be. So let's just focus first on benzene and tetrachloromethane. So I'm going to draw these out. So our carbon-chlorine bonds may have a slight dipole to them, but they're all going to cancel out because they're evenly spaced around that central atom. So we're only going to have London dispersion forces for that tetrachloromethane because it's just a nonpolar molecule. So we won't have a dipole-dipole interaction or hydrogen bonding. So this will just be London dispersion within a pure sample. And so this will be our, let's call our benzene the solute here. So this will be our solvent-solvent interaction. For our benzene, we have only carbon-carbon and carbon-hydrogen bonds. And so these are all nonpolar bonds, making the molecule itself nonpolar. So we'll also have only London dispersion forces. And these are our solute-solute interactions. So we're going to need to break these apart. So we're going to break all these London dispersion forces in both of these samples and bring them together. So when we bring these two compounds together to form a solution, so we'll call these the solute-solvent interactions. We're going to have two nonpolar molecules interacting with each other. And so they're only going to form London dispersion forces between one another. So right away, I could see that the forces I'm breaking apart are the same ones that I'm forming when I bring this solution together. So my initial thought is to say that this is an ideal solution. Now, if you came to the idea that maybe it's not, I see where, Now, our benzene molecule may be a little bit bigger than our tetrachloromethane, but those chlorine atoms are much bigger than a carbon or a hydrogen. So when I draw this out on paper, the benzene looks a lot bigger, but because those chlorines have larger volume than any of the atoms in the other molecule, we can assume that these are definitely different in size, but they might not be as different as we expect. I still think that the benzene will have slightly more surface area. And so you might say that it's going to have more energy to break those London dispersion forces than you would for the other one. At the same time, that high surface area molecule will be interacting with lots more of the tetrachloromethane molecules than in that case. And so it'll form a lot of those, a lot of London dispersion interactions anyway. So I think it's safe to say that we can assume this will be an ideal solution or close to it. Now let's look at the next one.